We have learned that a finite amount of power is lost in the switch in a power electronic converter. This power loss is converted to heat, which raises the temperature of the switch. The switches in power electronic converter are made of semiconductors like silicon, silicon carbide and gallium nitride. Each semiconductor material has a specific temperature range over which it exhibits the desired characteristics. Further, the electrical characteristics of semiconductor switches degrade with the rise in temperature. For example, the turn-off time and on-state voltage increase with increase in temperature of the switch, causing even more power loss. Therefore, the heat generated within the semiconductor switch needs to be transferred away to keep the internal temperature of the switch within safe limits. This is achieved by attaching a heat sink to the semiconductor switch as shown in this figure. Heat sinks are usually made of aluminum due to its good thermal conductivity, ease of manufacturing and low cost. The heat sinks are available in numerous shapes and sizes. A few of them are shown here. Most of the power electronic switches have a base plate made of metal or a material of high thermal conductivity to which the semiconductor material is connected internally. Heatsink is attached to this base plate through a thermal interface material which again has a high thermal conductivity. But electrically, the thermal interface material is an insulator. The heatsinks are firmly positioned with the help of screws or clips as shown here. As the power dissipated in a switch increases, the size of the heatsink also has to increase. For example, two power converters rated for 100 watts and 100 kilowatts will have different amounts of power loss even if the efficiency is the same. 99% efficiency of a 100 kilowatt converter means that the heat generated due to 1 kilowatt of power loss needs to be transferred to the ambient, which is accomplished by the heatsink. Therefore, heatsink is one of the significant contributors to the volume and weight of a power electronic converter. Magnetic elements such as inductors and transformers followed by capacitors are the other significant contributors to the volume and weight of a power converter. The effectiveness of heat transfer can be improved by attaching a fan to the heatsink, which is known as forced air cooling. The airflow rate can be adjusted to achieve the required heat transfer coefficient. In high power converters, typically with ratings more than a few tens of kilowatts, liquid cooling is also employed where a coolant is circulated through copper tubes embedded within the heatsink. An example of liquid cooling is also shown in this slide. Liquid cooling is also of importance when it is needed to build a power electronic converter with high power density. What is power density? It is the ratio of the maximum power that can be processed by a power converter to its volume. The units of power density are watt per meter cube. So how do we choose the size of the heatsink in a power electronic converter? The other components in power converter such as switches, inductors and capacitors are selected based on the required voltage and current ratings. The switches might be selected based on the conduction and switching laws in addition to the voltage and current requirements. But the heatsinks need to be selected based on the power dissipated in a switch, the thermal conductivity of various elements in the heat transfer path and the safe operating temperature specified. Let us try to take a closer look at the heat transfer mechanism to arrive at a simple thermal model which is widely used for the design of heat sinks in power electronic converters. We know that a switch in a power electronic converter needs to block certain voltage when it is in off state. This is achieved by an electric field within the semiconductor switch, which is due to the ionized atoms across a junction. And this junction is usually between a p-type semiconductor and an n-type semiconductor, or a metal and an n-type semiconductor. The junction within a semiconductor is considered to be the point of highest temperature. The maximum junction temperature that a semiconductor switch can withstand is one of the important specifications given by the manufacturers. Typically, the switches made of silicon have a maximum junction temperature of 125 degrees centigrade while those made of silicon carbide can operate up to 175 degrees centigrade. From reliability perspective, a power converter is usually designed such that the junction temperature is 20 to 40 degrees less than the maximum allowed under the worst case conditions. An example of worst case condition could be the power converter delivering its rated output power continuously 24/7 at an ambient temperature of 50 degrees centigrade. So we know the two endpoints in the chain of heat transfer. The ambient temperature on one end, point A, and the junction temperature on the other, point J. Let us define two intermediate points whose temperature is of interest. Temperature of the case of the semiconductor switch, which is denoted by theta C, and temperature of the heatsink surface denoted by theta S. The assumption here is that the temperature is uniform at all the points on the surface in which the point C is considered, and the surface considered here is the surface which is normal to the direction of heat flow. Similar arguments are true for points S and J. So this assumption of uniform temperature helps us carry out analysis in only one dimension. Let's try to understand the mechanisms of heat transfer here. The heat transfer happens through conduction from the junction to all the way up to the heatsink surface. It's predominantly conduction. From the heatsink surface to the ambient, the mechanism is convection. Let us take a look at the conductive part of heat transfer, and specifically between the junction and case. If we write the heat balance equation for this part of heat transfer, the heat generated in the junction is equal to the heat retained in the junction plus heat transferred from junction to case. So if P of T is the power loss in watts and P dt is the energy, the heat energy that is generated in the junction over time dt, and ms d theta j is the heat retained in the junction, where m is the mass in kilograms and s is the specific heat capacity in joule per kg Kelvin, and d theta j is the increment in the junction temperature over time dt. And the second term on the right hand side is the heat transferred from junction to case. This is again happening through conduction. So if we assume a linear temperature profile from junction to case, it can be expressed as lambda times Aj by d, which is multiplied by the temperature difference of theta j minus theta c. And Aj is the cross sectional area as shown in the figure, and lambda is the thermal conductivity of the semiconductor material, whose units are watts per meter Kelvin, and d is the distance between junction to case in the direction shown in the figure. Now rearranging the terms in the heat balance equation, we can write P is equal to ms d by dt of theta j plus lambda Aj by d multiplied by theta j minus theta c. So if we assume this theta c, the case temperature, to be constant, and we define a variable theta jc which is equal to theta j minus theta c, we can rewrite the above equation as P is equal to ms d by dt of theta jc plus lambda Aj by d multiplied by theta jc. Many times it is easier to deal with electrical circuits, so we try to look for some electrical analogy for this thermal process, and we have an equation written here: I is equal to C times dV by dt plus V by R, which is similar to the equation, the heat balance equation that we wrote. And what is the value of C here? C is denoted as CTHJ, that is the thermal capacitance, whose units can be joule per Kelvin or joule per degree centigrade. And then we have dV by dt, and what is this voltage? Voltage is nothing but the potential difference, and here in terms of the heat transfer, it is the temperature difference between 2 points, theta j minus theta c, is analogous to potential difference, and I is the current, which is analogous to P, power loss. And the second term we have RTHJC, thermal resistance from junction to case, which is expressed as D by lambda Aj, and whose units are Kelvin per watt. So if we just consider the heat transfer from junction to case, the top equivalent circuit on the right side represents the mechanism, and that gives us the thermal model. So the same can be extended for further points in the thermal chain. So we have case to sink transfer, heat transfer happening next. So a similar analogy can be made for the thermal capacity of the case and the thermal resistance between the case to ambient, so which results in the second equivalent circuit. And then comes the sink to ambient part, which is predominantly convection. So by using Newton's law of cooling, one can derive the thermal resistance from sink to ambient, which is shown in the third figure. However, for the purpose of designing a heat sink, the steady state temperature rise is good enough, and it can be calculated in a straightforward manner by omitting these capacitances from the circuit and including only the resistors, the thermal resistance values RTHJC junction to case, RTHCS case to sink, and RTHSA sink to ambient, and these are usually specified by the manufacturers. For example, any semiconductor switch manufacturer will specify the value of thermal resistance from junction to case, and when we choose a thermal interface material like sill pad, the manufacturer again gives us the thermal conductivity at least, from which we can estimate the thermal resistance. And then the heat sink thermal resistance RTHSA, that is again specified by the manufacturer. In fact, some manufacturers give the variation of RTHSA against different convection conditions. So natural convection, what will be the thermal resistance, and forced convection with a particular flow velocity, and when the flow velocity is increased, airflow velocity is increased, what will be the thermal resistance. All these data will typically be given by the manufacturer. So we will be choosing a heat sink which has the required thermal resistance value, because we would have already chosen the device and the interface material. So once we choose the device, the interface material, we have to choose the one with the lowest thermal resistance value, and with these resistances given, we have to choose an appropriate heat sink having the required thermal resistance value, so that the steady state temperature is limited. That means the difference between the temperatures theta j and theta a is limited to some given specification by the manufacturer. For example, at an ambient of 50 degrees, also our power loss should not rise the junction temperature to more than 100 degrees centigrade. With such restrictions, we can come up with the value of RTHSA, and by knowing the value of RTHSA, we can go to the manufacturer's data sheet and choose the required heat sink. Heat sinks are usually attached to semiconductor switches in a power electronic converter. However, losses occur in other circuit elements such as inductors and capacitors, which are also dissipated as heat. Fans or blowers are placed in an appropriate manner to transfer the heat generated by the other circuit elements. Refinements in the design can be incorporated by considering more detailed models of heat transfer. One can also solve the differential equations that describe heat transfer numerically using a finite element solver and arrive at an accurate temperature distribution, which helps improve the design of a power electronic converter. Such practices are usually followed in industry. So that completes the module 1 of this course. So to summarize, we have seen the need for power electronic converters. We have understood why we need power electronic converters, and that is because of the dissimilarities in voltages of sources and loads. primarily because of that. And we also have understood the notion of AC and DC in power converters. The AC waveform is a waveform with zero average value, while a DC waveform is a waveform with non-zero average value. However, both are periodic waveforms. And then we looked at the basic elements of power converter circuits or power electronic circuits. We have understood that switches, inductors and capacitors are the most basic elements. And then we intended to analyze the power converters in periodic steady state. So we understood the principles of periodic steady state, and we have also understood the measures of periodic waveforms, which are useful to quantify the periodic waveforms which are found in power electronic circuits. And we looked at measures in time domain such as average value, RMS value, peak value and so on. We also have looked at the measures in frequency domain, primarily given by Fourier series. Then we looked at the losses in the elements of power converter, more importantly the losses in semiconductor switches, both conduction loss and switching loss under different loading conditions. And finally, we looked at the thermal management of a power converter. How do you handle the heat that is dissipated due to the power losses that occur in the converter? We understood how to design a heat sink for a given semiconductor switch in a power electronic converter.